So now I'd like to ask some questions to you. The first one is what evolution do you anticipate in the next 10 years in the field of quantum science? So first, Akira, I'd like you to share your views on your photon-based quantum computers.
Yes. So we can prepare the hardware, and the next step should be the application of that one. And I think the most promising application would be neural network. And that is because neural network is analog computing. And quantum computing is also analog computing. So it is very suitable. And now we are trying to use our quantum computer for quantum neural network. And the one reason is that for quantum neural network, we don't have to have quantum error correction capability because brain does not have any capability of error correction. So we should use our quantum computer for quantum neural network. That is my opinion.
Thank you. Exciting, the keyword quantum neural network. So, but can I ask a very short question? Basically, the neural network, non-linearity is very important. But basically, quantum mechanics is very linear work, right? So, how do you feel the gap between these?
Okay, very good question. Actually, this year we succeeded in making non-linearity for quantum computing. And it is electrical circuit based.
Oh, you combine the two.
So, yeah.
I see. Thank you.
Yeah, so we developed electrical circuit to create nonlinearity for optics. And it is FPGA based. And now we are trying to make ASIC.
Oh, I see.
And the bandwidth should be can be 20 gigahertz.
Thank you very much. Ulrik, I think your field is very similar to Akira, so could you add something to his take?
Yes, I completely second what Akira was saying. I mean, we are using the same technology, it's the same platform, so I also believe that this is the way to go, of course. I mean, we have seen a number of breakthroughs within that field. I mean, on photonic quantum computing, using different platforms for photonic computing, we have seen a increasing number of breakthroughs in recent years, but also in other platforms we have seen important breakthroughs in terms of demonstrating quantum advantage was done on a photonic platform, but also on a superconducting platform. And also the demonstration of quantum error correction beyond the break-even point has been demonstrated now. Fantastic results. So there's a number of groundbreaking results that are popping up these years, and I think this will just increase in the future with the support we're getting in that field here. So, but this is only quantum computing. I mean, of course, there's also quantum communication and quantum sensing. So here, I think. In particular on quantum sensing, I think we will see in the next 10 years that you can go buy quantum sensors with a practical quantum advantage because I mean the field is much more mature on quantum sensing than in quantum computing. Quantum computing here you will also see a practical advantage I think in a few years using a NISQ type of computer, but the fault tolerant universal quantum computer, I'm not sure whether you will see this within the next 10 years, but so this, I mean, here we have to maintain some long-term vision, and yeah.
How long do you think?
I mean, maybe 2 decades. So the Novo Nordisk Foundation is supporting a program on universal quantum computing, and I think this is a 12-year program, so maybe in 12 years. I also know there's a moonshot program in Japan, and I think they're targeting 2050. So that's further ahead.
The funding is very important for such a very long-term research. So I'll go back to this funding problem, but before the Tsuyoshi, so you are specialist in the superconducting-based qubits. So can you share your vision in the what happens in the next thing?
Okay. Yeah, I think there are two aspects, points. In superconducting qubit, the qubit must be cooled down to almost absolute zero temperature using a special refrigerator called dilution refrigerator. And because of the limitation of the space and the cooling power of the refrigerator, it's difficult to integrate the qubits. Present approach achieves already 100 qubits. That's great, but it's a kind of brute force approach. So there will be a limitation, maybe 500 or 1,000. But that's great. In 10 years, the number of qubits will be increased, and the NISQ application, NISQ machine will become very, very improved. And but the important point here is that we need to find some useful application using that 100 qubit, 500 qubit machine.
So you don't know any application yet?
Useful application. That's very important because if it's not found, for example, in 10 years, then the private company may lose interest, so they may stop the investment. And that's not good. That's a bad situation. So that finding a useful application is very important.
Useful is very important.
Yes. And another one, the Fortran quantum computer. So we need much more number of qubits. So brute force approach does not work anymore. So but we don't know presently. We know that we need some breakthrough technologies, but it's not yet known. So if we can find it in 10 years or not, that's a very important point.
So we learned that it is a long way to make the quantum computer really useful. So first we have to make the error-tolerant quantum computer hardware, but at the same time we have to something useful to make the quantum computer can be applied to. So it sounds like a very long journey. So maybe more than a decade, something more long research. So for such a long-term research, funding is very important. So could you share your vision on the what kind of funding should be made for the future quantum research and application? So can you say vision?
Yeah, thank you. First of all, I think it's important to be patient. And that is difficult because, of course, we are all really excited, both the researchers and the ministries and the foundations, but it's really the long haul that we are after. And it's difficult, and there is an international competition, which means we really need to be on our toes and go, be ambitious. And I think from a funding perspective, it's a huge investment. It's a lot of money, and it will only pay off after a while. And also, it's an area where it's very difficult to be VC. So to be, the brave person who puts in the capital needed for all these wonderful startup companies to get their Series B, for instance. And so, therefore, it's an area that is difficult to get into if you are not a quantum technical expert, and even if you are, typically your area of expertise is relatively narrow. And being an investor, it's even more difficult to make the judgment of, is this hot air? What is it? How good is it really in comparison to the competitors? and all these judgments where there is a lack of experts in the investment area who can make these judgments. And I think we really need actually good experts from quantum to go into investment, because we need that capital to bring it on. And we need a time scale which is, say, 10 years, 20 years, maybe even 50 years. But in addition to that, I think it's important to keep the sight actually on the applications. Because sometimes the applications, say in pharma, say for instance for accelerating drug discovery, for developing precision medicine, where you have very noisy data, actually the application could be important for your choice back on the technology. So for instance, exactly what type of quantum processing unit is most advantageous for a particular application, what type of electronics, of course the algorithm, etc. But all the way down to the hardware, likely choices need to be made that will depend on the application. So therefore you need to think, it's like a moonshot, it's really a moonshot. You need to think, okay, I need to reach that goal, how do I do that? And that will imply certain choices already today.
Here that the Novo Nordisk Foundation has a very big pharmaceutical functions, companies. So what is the length of research in the pharmaceutical research? Is it longer than the quantum or shorter than it?
Yeah, so actually, it, to my knowledge, going from having a target to having a full product on the market takes even longer. So the pharmaceutical companies typically look into timescales of, say, 25 years. So with a pharma background, the timescale of quantum seems quite reasonable. Yes.
Yeah, so the quantum mechanics was born at the Niels Institute about 100 years ago. So yeah, we have used about 100 years to gain the full understanding of the quantum mechanics. So what do you think we should do next from the basic research point of view and the funding point of view?
I think we're doing a lot of the right things right now. A lot of the initiatives that we see worldwide are spectacular. One of the things that we have been focusing on in Denmark is the public-private collaboration that you can establish, which I think is an important thing here. As Lene also says, this is a long journey. We don't know how long it is right now. Maybe 50 years is overshooting a little bit, but it's definitely out in the future somewhere. So having strong public-private sort of partnerships, I think, is an important thing for us to develop further these things here. I think for funding into quantum science these days, important that we keep on funding basic science, because basic science will give us all the ideas that we will have in the future for new sensors, for new quantum resistant equipment and communication equipment and so forth. Also on the simulator and the quantum computer side. We don't know which platform will win. We have no idea. We have very good ideas. This is what is fascinating in my view of this, looking back at the 100 years, that we have neutral atoms, we have ions, we have superconducting qubits, we have spin qubits, we have photonic circuits. There's so many different platforms. Some of these platforms will for sure gain advantage at some stage and really move through. Doesn't mean that the other platforms are not interesting. They could be interesting for other purposes that could be tailored together with HPC. We are looking into GPUs now that are looking a little bit more different than what we did before, quantum QPUs that are going to be merged together with this platform. I think that's the interesting thing for us to look at. While waiting for the full tolerant computer, there's a lot of things to be done on simulations that we can already do right now. And you see spectacular results coming out on understanding small molecules like water and so forth. Even lithium hydride has been attacked also and giving spectacular results. There's a lot of things that we can do on waiting. And We will see if we will wait 20 years or 10 years or 15. We don't know right now, but there's a lot of things to be done in the future. Yeah.
May I comment? I mean, just a small comment. I completely agree with what Jan is saying, that it's super important that we also keep supporting fundamental research, because it's really a long-haul vision we have. So we have to maintain this long-term perspective. But I think it's also important that we diversify the investments. So I mean, there's a long chain from the fundamental ideas to commercialization, and this chain consists of many different links, and every single link needs to be supported. So, I mean, fundamental research, but also the commercialization is also important to support this, because, I mean, we have many different types of technologies. Some of them are very mature, some are not that mature. So,
can I leave a comment?
Oh, sure, please.
Okay. So as the position of program director of SIP program, I want to give another comment. And in the history of quantum mechanics, MR is very important for its application of MRI measurement.
Yes.
It's very effective for human life.
Yes.
So for long, high-level investment by government or private section, we must show some effective results, not 10 years later, within 10 years. So this means quantum sensing is very important in these 10 years. For example, medical application or healthcare application. So microparticle diamond with NV center combined with drug materials judge the effectiveness of medicine. And also carbon-13 NMR is also very important to this purpose. So we need to continue keep the research on fault-tolerant quantum computer, but we must consider the quantum sensing field. This is short, not long-term purpose important.
So it's a measurement inside the cell of our bodies. Thank you. Yes.
I completely concur. I think there's the quantum computing platform, which is one platform that takes a long time. But then there's, of course, also the sensing as brought forward, and also the quantum information. And they are, as you also mentioned, Ulrik, they are a lot closer to market than a lot of the other technologies that we are discussing this afternoon. There's such a big potential in quantum sensing. I mean, the biomagnetics of that is super interesting in our view. Combining biomagnetics with the molecular markers, magnetic markers, that will give you possibilities, I think, for phenotyping different drugs in a completely different way than we are doing today. So I think sensing on timing, on position, on forces, on pressure, on rotation, on gravitational field, there's a huge commercial potential there that we should not overlook. Completely concur.
The research in the field of material science is very important in that direction too. Thank you very much. So finally, but it's a very important question. So I'd like to ask about your collaboration between two countries. So now we have the fantastic scientists from these two both countries. So what do you expect the collaboration between Japan and Denmark? So first, Akira, so what do you expect for the collaboration?
As Ulrik said, we already have 20 years experience of collaboration, and it worked well. The reason was totally different.
Totally different.
So from Japanese sense, we are looking from this side, but Danish sense from backside. So that type of combination is very important for science.
So do you mean the approach is not same?
Approach is different, and the way of thinking is totally different, I should say.
Yeah, I'd like to hear your take on this. Ulrik.
I agree that it's the differences that makes a good collaboration. I mean, we are using the same technologies, the same platforms for realizing quantum computing, but but maybe our approach to it, the way of thinking about it is different, and maybe that has created this fruitful collaboration between the two of us for that many years. So this has really been a big enjoy over those years, having those collaborations. I think another collaboration that I think could be very important in the future is collaborating on the infrastructure. I mean, development of materials, quantum materials, because there are many different types of materials that we have to develop further. I mean, one example is diamond, because I like diamonds. I mean, I was visiting AIST yesterday, and they're growing diamond with exquisite quality, making some of the best diamonds in the world, and of course we'll be happy to collaborate with this organization on this. And we also, for example, at TU, I mean, we have also fabrication facilities. For example, we develop silicon chips headed by live oxen liver, making some of the best silicon chips in the world. So that could also be a way of collaborating with scientists here in Japan.
Yeah, in Japan, the spectrum of the material scientists is very, very rich, from the nanoparticle to the correct and lectin system. So they are very rich spectrum of the material science. I'm sure it can contribute to the world community of the quantum science. Okay, please.
So maybe I step up into the helicopter and take a look, and then I would say, yes, it's very important with collaborations on strategic areas like you are describing. I think in addition to that, it's really important that there is a ministerial connection between Denmark and Japan. That is going to be crucial for establishing such collaboration, also for making it easy for the researchers to move back and forth and to prioritize the collaboration. And then, of course, in addition to that, there's also the question of funding the collaboration. And here, I think it's good that more parties have skin in the game. And of course, here we would also, from the Novo Nordisk Foundation side, be interested in enabling such research collaboration. And I think actually one good way to start is with the young talents. With, say, master student level or PhD student level, potentially postdocs, and have an exchange program where students can go back and forth, get experience from working in the different countries, seeing the best of both worlds. I think that would be really helpful looking forward.
Wonderful, wonderful. Yeah, education is also very important to reinforce the area of scientific communication. So, Akira, I hear you are using the laser system made in Denmark.
Yeah.
So why you choose the laser made of Denmark? So could you comment on that?
That is very simple. It is the best.
Best, oh. How do you like it? So,
yeah, very much. Yeah, I like it.
Mm-hmm. We're happy.
From the cooperation point of view, what do you expect for the collaboration between Japan and Denmark?
I'm now consider a different culture or society. For example, Akira will start a new startup company, but in general, in Japan, we have a small number of startup companies, especially hardware, quantum computing field companies. A few, very small. But I think in Denmark there are some or many hardware startups. So complementary role is very important, I think.
Okay, thank you very much. So it's almost time. So in hope of further advancement of quantum science, I'd like to conclude this session. Let's thank all the speakers again. Thank you very much.